Dear committee members, good morning. Thank you for this opportunity to present my PhD work to you. My PhD title is Context-Aware Navigation for Safe and Efficient Maneuver Control of Moving Objects in Cyber-Physical Systems. I'm Aime Mugabarigira, and I did this work under the guidance of Professor Jaehoon Jung in IoT Lab. For this presentation, I described the background of this work, and also I present the three chapters to say context-aware navigation protocol for safe driving in vehicle cyber-physical systems, and I also present the collision avoidance navigation algorithm for UAV flying network with heavy traffic, and lastly, I will present the machine learning assisted self-adaptive interactive navigation tool for efficient parcel delivery neural networks. Recently, there have been several advancements in the area of autonomous driving. Vehicles currently are equipped with several sensors, enabling to have several available data which can be used to decide and take intelligent decisions for driving. This has made possible for several advanced driver-assisted systems, such as collision warnings, lane control, emergency braking, path maneuver, cooperative decisions. Indeed, in the area of urban air mobilities, UAVs have also been advancing. Several applications have been deployed, and several mechanisms have been put on in order to avoid collisions, such as screening flights, low altitude flights, so that you can fly only in the line of sight of the UAV, and also piloting, where you monitor and control all UAVs despite the fact that they can be equipped with autonomous flights. Short-term conflict alert separating, so they have airborne collision avoidance systems. In this work, first we did a context-aware navigation protocol for safe driving in vehicle cyber-physical systems. In this work, we try to take advantage of the current advancement in the presence of several sensors in vehicles, and also the availability of network infrastructure such as roadside unit, which are enabling the vehicle to infrastructure and infrastructure to vehicle communication, so that we can use such kind of available information to assess and discern the risks in the road and be able to take decisions, and also enabling vehicles to cooperate so that they can be cooperatively sensing and getting the awareness of the driving environment and having the obstacle identification, and together and collaboratively collaborate for maneuvers and the controls. This work, we are trying to handle the scenario of collisions. We have been able to see that road accidents are causing as one among the top 10 causes of deaths in the world. More than 1.2 million people are killed every year for road accidents, and more than 50 million people are injured every year. And what you have been noticed is that more than 94 causes of crashes are human-based. Human error, distractions, and so on. So, in other words, the other factors such as environment, vehicles, failures, or unknown reasons share only 6% of the accidents which are there in the road. This means by ensuring the autonomous handle of driving, we can be able to solve more than 94% of road crashes, and we can be able to avoid collision in the road, therefore ensuring the most safe driving in road networks. In this work, we try to design a mechanism that can handle scenarios such as an accident, for example, such as abrupt stop of a vehicle in front of the sequence of vehicles, and once it abruptly stop, the next vehicle which can detect this obstacle can share the information across the network, and the vehicles can be able to collaborate so that they can avoid collisions. And also, once collision happen, we try to limit the damage by limiting the number of collisions and by limiting the collision strength. In this work, we are using local sensor data for sensors of the vehicle, and also we are using the remote shared kinematic information and sensitive information, which we are calling remote sensing. And once we receive such kind of information, the mechanism runs the risk assessment to discern and identify the possible obstacles in the road network. And once the obstacles are detected and identified, the possible collision avoidance modalities are analyzed, and the vehicle can be able to detect the movement. Because vehicles are driving into clusters, a cluster head can be able to be the one to handle this calculation to avoid the calculation load. Indeed, once the calculations are made and the maneuver are identified, vehicle can do either lateral or longitudinal maneuvers by ensuring the avoidance of the obstacles. In this work, vehicles, as we mentioned ahead, vehicles are collaboratively coordinated through cluster head to avoid collisions. And we designed a probabilistic based collision avoidance and the risk assessment mechanism which calculates the risks of colliding into lanes so that we may be able to detect the most safe lane where a vehicle can be able to maneuver. And this calculation is sequentially done, therefore trying to identify in each step which is the most safe lane to move toward. And for this, we invented a safe lane quality matrix, which is a metric for safety of the lane, which we calculate once we have identified an obstacle in the road. Once we have already calculated the safe lane qualities, we compare to the left, to the right, and in the emergency lane, and we identify which is the most safe way to take to avoid the obstacle. And the vehicle can be able to start by the most concerned vehicles, which is the emergent vehicle, and toward the most real vehicles, avoiding toward the most safe lane in the road network. We assess the performance of these calculations, and we realize that once we calculate with the more hops in the road network, we can be able to more intensively and more significantly get the slowest probability of collisions in the road network. However, the more we consider the more numbers, such as for example in this figure we are considering 8 hops. Once we consider multiple hops, we can end up having much computation. Therefore, we limit by using only 4 hops so that we limit the computation risk. However, we can be able to identify that the collision at the collision probability at the fourth hop is smaller enough, is closer to 0.1. Therefore, can be able to identify the obstacle and be able to provide the most safe lane quality in the road network. In our calculations, we try to analyze the performance of our CNP algorithm compared to network collision avoidance system and sensor-based systems. And for the networked systems such as CNP and NCAS, we realized that CNP can reduce up to from 15 to 60% of the communication overhead and provide the safe, be able to analyze the safety to the level or much better of the NCAS. In here, it's also for the number of speed we compared. It is we significantly reduce the number of packages we can be able to transmit. On the left hand, we can see that CNP is having the smallest risk once we compute using our mechanism, and we can be able to identify the most safe lanes to avoid the obstacles in the road network. By comparing the different injection rate in the road network, we identify that CNP is providing the most smallest collision probability compared to the baselines. And we can also confidently mention that networked systems such as NCAS and CNP provide much better safety compared to the other baseline such as network systems. And such as the Thesis-based system. And here also we can identify that this CNP is providing the lighter collision strength once collision happens. And also in the number of speed compared, we can see also it is having the lightest collision probability, collision strength compared to the baseline. And for this, by comparing also the accelerations, we can realize that CNP is providing the smallest collision probability compared to the baseline. And therefore, we can say that CNP is the better mechanism for risk assessment and collision avoidance more than the baseline we compared. In this work, we presented the context-aware navigation scheme for safe driving in vehicle cyber-physical systems. CNP provide autonomous vehicle with a collision-free navigation service under either high congested highway or emergency situations such as road accidents. CNP take advantage of vehicle networking for cooperation driving. CNP use a probabilistic graph model to measure possible collision during maneuver, control, and vehicle navigation. The second work we did collision avoidance navigation algorithm for UAV flying network with heavy traffic. We can see the recent progress of application which are using UAV, such as for example in medicine there is such as blood delivery in high mountain areas and remote areas. Parcel deliveries, Amazon and Google are predicting to use drone for parcel delivery, and disaster management and search and rescue. Drones are mostly used. Such kind of risk is one where human can be put in danger, and it's more deployed for cinematography, for image and video recordings. Several network facilities also are available, enabling UAV to communicate among themselves. Therefore, we can use those network information to control flight, because uncontrolled flight can lead to multiple collisions in the area, and then a shared UAV collision incident can lead to several sequences of collisions once several UAV are deployed in the network. How can we avoid mid-air collisions? First, in the literature, the most used scenario is by screening the flight, where only the allowed flights are allowed to fly in a specific airspace. And another mechanism they are using to avoid mid-air collisions is that once you are flying your own drones, you may fly at the line of sight so that you may avoid collisions. And another possibility is by piloting or short-term conflict alert and separation of airborne collision avoidance systems. But a lot needs to be done to be able to deploy massively drones or UAVs in the urban area. So in this work, we are trying to assess what can it take and what can we do in order to enable several missions, for example, the mission from the base station 1, 2, 3 to M, be able to deploy the drones in the same airspace, in a shared airspace, and be able to fly by avoiding accidents and within and by also without sacrificing the mission it is aimed at. So in this network, we advocate the use in this work we advocate the use of 5G enabled UAV communications and support the vehicle mobility information sharing through 5G V2X communication. We enable lightweight sensing information sharing by sharing the cooperative context messages and the emergent context message once the identification of emergent scenario in the areas. We designed a multiple layered space so that the airspace is a 3D sky split into multiple layers, where each layer can be considered as a 2D road network, and each layer represents a UAV flying at the same heights, and therefore we can be able to fly safely and also try to sense the information, share the information among neighbors, and analyze the risks and provide the collision avoidance through aerial vehicle mobility updates. In the same layer, we try to provide a road-like virtual road-like in multiple layer flights, therefore providing lanes and be able to move up and downs, but providing also safe ways to move to the left, to the right, and in the area toward the destination of the mission. And we designed a 5G enabled kind of communication between drones and ground control systems, where this figure 2 is representing a 5G V2X protocol stack, allowing the UAV to communicate among themselves and UAV to communicate with the ground control systems. Once we have the kind of graph, we can be able to design a graph like network, enabling to prepare or provide the path planning by providing the shortest path, geographical shortest path, and safe paths by providing the safe gap among UAVs. We provide also the safe path planning for mission and a safe flight while handling the mission toward the destination by predicting congestions and also by avoiding collisions and by moving and modeling the landing and takeoff toward the destination area and at the base stations. This kind of landing and taking off is based on volumetric path planning mechanism, where one voxel can hold safely one UAV. Therefore, we try to move while landing. We move a drone in a way that in this way, a voxel is occupied by a single drone at a time, avoiding simultaneous use of voxels, therefore enabling to be safe while landing and while taking off. We provide a probabilistic risk assessment in a virtual road network, where we analyze the safety in the emergence layer or emergence lane. We have three possibilities to move to the same directions, change to the left, to the right, and also be able to move toward the upper and to the down, therefore providing 5 possibilities to move a vehicle. By using the safe lane quality, we can adapt this to a 3D scenario, and we can be able to analyze the safety of either moving to the up, or to the down, or to the left, to the right, or to continuing to the north or to the south area of the same layer. And therefore, we can be able to determine where a UAV can fly toward to avoid obstacles. We assessed through simulation in the Omnet simulation, and we can be able to see that similarly Canna can provide can reduce the number of overhead required for communication in order to communicate the scenario in UAV network. Similarly, for the different number of speed we tested, Canna is providing the smallest number of packets to be able to disseminate the scenarios and the information in aerial airspace. We assessed the impact of UAV speed in the case of a static obstacle, and we can see that in all tested number of speeds, we can see that the Canna provide the smallest average probabilities compared to the baseline, and also it can provide the safest lane quality compared to the baselines in both scenarios. We can assess also the impact of speed deviation, and for all the speed deviation we compared from 1 to 10, you're going to see that Canna is providing the smallest average probability compared to the baseline, and also is providing the most safe lane quality compared to the baselines, either in the emergence or while moving to the upper and down layers. We compared also the impact of Canna on position error, and still we can see that it is providing the smallest collision probability compared to the baseline, and it is also providing to the right the most safe lane quality compared to the other baseline. In this work, we studied the collision avoidance navigation algorithm for UAV flying network with heavy traffic, and we designed a heterogeneous UAV flight enabling collision-free UAV navigation service under congested airspace. And we propose a network structure-enabled UAV to horizontally fly in different altitudes and provide a road-like virtual aerial lane enabling UAV to safely fly. And also can take advantage of 5G enabled communication for cooperative flights. Can I propose a probabilistic graph model suitable for a 3D UAV flight trajectory to measure the possible collision during UAV control or sharing through system synchronization. The simulation-based result also show the superiority of CANA. Lastly, in this work, we are also, in this thesis, we worked on machine learning assisted self-adaptive interactive navigation tool for efficient parcel delivery in rural network. In the background, the graph neural network have been deployed, have been studied intensively recently to explore the graph nature of data and try to assess the similarity and estimate the possible similarities that may influence the performance of graphs. This enabled for trajectory planning and route planning and also route structure predictions and mission planning that can be able to enhance the traffic forecasting in the road network and also in the airspace. In this work, we are trying to study the effectiveness of graph neural network on road traffic forecasting so that we can be able to efficiently plan the routes and manage and update driving information over time for traffic performance optimization, increasing the driving accuracy by reducing exposure to congestions, and easily extensible integrating new challenge. That is one among the benefits of graph neural network, and update vehicle path to complement and interact while driving in road networks. In this work, we are trying a scenario where we are sure of the presence of large traffic database because of those sensor information shared, network shared, information, driving information shared, and we can be able to have more large database which we can learn the road trajectory, and we can be able to train the models which can help us to predict the road congestion and be able to plan the efficient routes. And we can be also to provide with connected vehicles the possibility to autonomously select better paths and avoid obstacle, and can be able to cooperate by sharing the information with the infrastructure networks. And for the route planning, there are two possibilities. There are statistical methods or machine learning methods. In this work, we try to plan the road trajectory of vehicles in a way that can enhance the estimated time of arrival of parcels delivery for a cargo. We are taking advantage of the SENT navigation mechanism. SENT is a self-adaptive interactive navigation tools, is an algorithm or a mechanism developed to maximize the throughput of road traffic flow and minimize the travel delay using vehicle trajectories. And here the aim is trying to limit the use of geographical shortest path, because usually when a vehicle trajectory in navigation is done by using the shortest path, route is likely to keep on being stacked with several vehicles, therefore leading to congestion. For example, this graph for trajectory 2, while keeping the trajectory 1 so light without vehicles. So we try to design a mechanism which can also sacrifice the length of trajectory but limit the congestion, therefore improving the throughput, improving the delay of trajectories. This is what we are trying to do, and the graph neural network, what we do is we take a graph and we train it several times through the graph convolution layers, and through this kind of training we can be able to learn similarity between different nodes. How many vehicles can, for example, move from node 1 to node 2, or with more training data we can get, you can see how many left from node 1 can end up going to node 6 because we can learn several similarities. So in this, we can have several traffic data collected through the loop detectors and the cameras, and we can model the graph convolution network so that we can learn the geographical shortest path or the delay aware shortest path by using those kind of trained data. And therefore we can efficiently estimate the time of arrival or the origin to destination time estimation. For the spatial temporal graph convolution network, what we are trying to get is the spatial dependencies and the temporal dependencies. For at a given, especially at a given position, how many and how far the traffic at a node at a specific junction can end up influencing the neighbors or the 3 hops away kind of other junctions. These can be studied, and by using the input data such as arrival rate, last step time number, mean speeds, we can be able to capture and extract spatial relationship and temporal relationship, and therefore use these to estimate the shortest path in terms of delay, one which will take the shortest time as possible, so that we can meet the parcel delivery deadlines. ML-Cent we are having a self-adaptive feature aggregation mechanism where we keep on updating the nodes and studying the dependencies with the neighbors through the vector representation, how each node relate to each other. And by narrow message passing, we can learn how much influence we get from one node. Therefore, we can be able to predict the traffic in the near future by using the information we have in the network. Within this work, we simulated this work in Sumo, and we trained it using Sumo, and we can be able to train data and extract the feature like pending vehicles, injection rate, travel time, which are the data we can be able to extract via Sumo. And we train the graph to know the graph representation and be able to detect the delay aware constraint shortest path, and by taking advantage of Cent algorithm. So with the training and the performance we did show that using the machine learning mechanism can significantly improve the delay, the average link delay and the end-to-end delay in the road network. For example, for all the tested number of destinations, we have identified that ML-Cent can improve up to 42% of link delay of Cent. And it is clear that the machine learning approach, such as either linear regression model or our graph convolution model, is providing the best average link delay compared to the baseline. And similarly, also in terms of end-to-end delay, it can improve up to 2.6% of the average end-to-end delay compared to the statistical based Cent. And also we compared with the number of vehicles. These are the vehicles which we consider like cargo, because we have more than 1,500 vehicles running in our road network. And we are trying to see how much can it be improved, and we can say up to 25% deduction of the average link delay is provided by ML-Cent compared to the statistical Cent. Similarly, also it provided up to 26.5% in improvement of the end-to-end delay compared to the statistical based Cent. And also for the simulation of maximum speed, also we realized that ML-Cent can improve up to 22% compared to the statistical based, and also it can improve the end-to-end delay up to 19% compared to the statistical Cent in all maximum speed we compared. And also about the acceleration, it can improve up to 45% of the link delay compared to the statistical base, and also in terms of end-to-end, it can improve up to 44% of average end-to-end delay of the statistical cent. Therefore, we can proudly mention that ML cent significantly improve the road traffic and also improve the prediction of the estimate time of arrival of parcels. In this work, we study machine learning assisted self-adaptive interactive navigation tools for efficient parcel delivery in road network, and it proposes a learning mechanism which learn the road features to predict congestion in road networks. Through delay-aware shortest path, we determine the cargo path which satisfies the parcel delivery deadlines, and the simulation-based evaluation along with performance result was provided in this work. This is my publication list, and this is also my patents and our conference. Thank you so much for listening to my presentation. Thank you.